Let me welcome you all here this evening. We should get started because we only have 13.7 billion years of history to go over tonight. You've heard about speak softly and carry a big stick. I don't know about the stick, but he's going to speak very quickly this evening. This is lecture 2 of Big History. I welcome you all here. How many of you were here last week? Good. So you come well prepared. My name is Craig Merlin. I'm the immediate past president of the World Affairs Council, and we are very pleased to have this series on big history, certainly a new concept to me until last week. We're honored that one of the world's leading experts on world history is here with us for all of the lectures. He is a professor at Grand Valley State University, and it is Dr. Craig Benjamin. As those of you who were here last week may recognize, it can be a little hard to understand him with his southern accent.
Hey, y'all.
But that may be Southern Australia. And he may be a little slow this evening because he had to spend all day today taking that test for the U.S. citizenship. I still think it's a touch and go matter. But with that, let me introduce Dr. Benjamin. There will be, as there was last week, a good opportunity for questions and answers at the end of his program, and we really had some very excellent questions last week as well after an excellent program. So I'm sure you will enjoy it this evening, and welcome, Dr. Benjamin.
Thank you, Craig. Thank you very much. Good evening, folks. A pleasure to be here again. I'm surprised you're not all at home watching Wolf Blitzer and the best political team on television and waiting for the latest exit polls from Cuyahoga County, West Virginia, or whatever's going to come up next. Very exciting night. It's somewhat ironic that my wife and I wanted to take out citizenship so that we could vote. And of course, here it is election day, and it's on that very, very day that we had our test. So it's been a long day. We've been up since 5 this morning at a hotel in Detroit, preparing ourselves, going over the 100 questions one last time. And then in this magnificent facility on East Jefferson Boulevard in Detroit, where there were hundreds of people lined up, and it's a very serious interview. Obviously, a lot of security to get into the building, and then you sit and wait your turn, and we were taken back one at a time to a room, and we were asked about 25 quite complex questions on U.S. colonial history and U.S. constitutional law and so on, and also had to be able to write in English. That was a challenge. The quality of my handwriting is not good, so I said, okay, if I print in capital letters. He said, I'd prefer that, sir. I'd prefer that. So I had to write that George Washington was the first president, and I think I passed that test as well. So at the end of it, he got out a big red stamp and said, approved. And he said, you'll be sworn in at the Gerald R. Ford Museum 2 weeks from tomorrow, on the 17th. So I tell you, it's been a long, nerve-wracking day for my wife and I, and then we've driven back, but we're very, very excited. It's a pleasure to see you all here. And this lecture is ridiculous. To try and cover this much history in an hour is crazy. Even in a regular big history course, this would take a month of classes. So it's at least 12-hour lectures to cover this. So we're going to try and do the impossible tonight and do some of this in an hour. I've had some very interesting correspondence with quite a few people in the audience from last week about big history, some very positive, some with some quite legitimate concerns, I think, about big history, about whether historians have a right getting into the world of science. Are you a qualified historian, Benjamin? A qualified scientist, physicist? No, I'm not. What right do I have then in sort of using scientific knowledge and approaching it in a somewhat general way? Some of the arguments I mentioned last week, I think, remain valid to me. That is, many students have never heard these major paradigms or theories of science explained to them before. They've never, ever heard them before. It struck me as staggering when I first realized this, but then I thought, well, it can do them no harm to at least have a reasonable idea of what these theories argue and what the evidence is for them, particularly if they're involved in intense theological debates over some of these very issues. So at the very least, a general appreciation can be of some assistance. I also think that the ideal way of teaching big history is a team-taught interdisciplinary course where you would have a physicist who would teach the first month, or the first, say, 2 or 3 weeks. You'd have a geologist, you'd have a biologist, and they would teach their specialized fields so that students would be hearing from trained professionals in those fields. As I mentioned last week, that's easier said than done in terms of timetabling. Becomes a major challenge in accessing professors, working out schedules and so on. However, at the Honours College at Grand Valley, where we will be teaching big history as a full year course, starting in about a year's time, it will be taught there as an interdisciplinary course. So students won't have a generalist like me doing his best to introduce these theories, and instead we'll have specialists able to do this. Having said that, every student at Grand Valley, and indeed at most liberal education universities, have to take a couple of mandatory science courses. A chemistry course, for example, a biology course, perhaps a geology course. These are theoretically general introductory courses, but quite often they're taught by specialists in their fields who tend to want to focus on teaching the disciplinary skills of that particular specialized field. In that sense, students come away from a class like Chem 115 or a Biology 110 with no real idea of the significance of what they've spent a semester doing. They've learned a few of the skills, but they have no idea what it means. I'm not saying all gen ed science is taught this way, but a lot is. When I've introduced big history to scientists, they've generally been far more accepting and welcoming of this approach than most historians have. Most historians say, this is not history. Most scientists say, wow, this is really interesting. I can see a real role for something like this in our introductory science courses, for example, as part of the science gen ed component. I think I also mentioned last week that a number of scientists have embraced big history, and we've got some of the world's leading geologists and physicists that actively teach big history courses at universities all over the world, including UC Berkeley, for example, so very high-quality schools. I just wanted to throw out those caveats first. The other thing to remind you is that big history is designed at two educational levels, for undergraduate first and second year students, right? And also now increasingly for K-12 students, particularly around 9th and 10th grade. So the sort of science that those students need to hear is science that is relevant, that makes sense, and that has some connection to their lives and to the human history story that follows in the second half of the course. If there are scientists out there tonight, you'll find these accounts too general for you. You'll learn nothing new. The rest of you, I hope, will not be as familiar with some of these accounts, these paradigms, and therefore might find it of some interest to hear them explained in a general sense, but with sufficient detail, I hope, to support the paradigms. So in the beginning is the question that we have to address today. And we take it from the very beginning, that point before which we know nothing, and we'll conclude today about 7 or 8 million years ago, right? So literally about 13.6 something billion years. We're looking at the most significant science there is, frankly, the major paradigms, the major theories that the extraordinary specialists in various scientific fields have been able to devise. I'm talking about physics and astronomy, geology and biology. And very briefly, as much as I can in an hour, let's look at the theory of the Big Bang and the evidence for it, a little bit about how this evidence came to light and led physicists almost unwillingly to accept this theory of the Big Bang, which is a term that was first applied very dismissively to this theory, which seems so bizarre, applied by the English astronomer Fred Hoyle. Then what do we know about stars and galaxies? Why are they significant in the human history story? I mean, for obvious reasons, our own sun is very significant to all life on Earth, but even more than that, in terms of the manufacturing of more complex elements in the universe. What's the role of stars in that? And then what do we know about the sort of solar nebula theory of solar system formation? And what do we know about our own early planet? If we had time, of course, I'd talk about the exciting search that's going on for exoplanets, for planets that are out there similar to our own planet, perhaps, in proximity to their sun, similar in size, perhaps. That search has gone from something like, 15 known planets just a few years ago to well into the 200s now. And only last week, an exciting discovery of a planet, I think it was 3 times larger than Earth, in a reasonable Goldilocks-type position, as I mentioned yesterday. Not too close, not too far away, just right. Unfortunately, we won't be able to go into that in any detail, nor will we be able to do any justice at all to that final topic. What does biology tell us now about not just evolution and Darwin's theory, which is now 150 years old, I guess, but the origins of life? How did life appear on this lifeless rock? This question begins then with how did it all begin? I mentioned last week and had an excellent conversation with Craig here a moment ago. Is big history almost theological in offering this alternative creation story? Creation is a very dangerous word, of course, but story of origins, story of planetary, of cosmic history, of human history. Every story has to address this question, though. How does it all begin? And every society that I'm aware of, and I've studied many creation stories, creation myths, have devised different ways of answering this. How did everything begin? You would all be very familiar with the Genesis account, of course, and that everything was created by an all-powerful deity. In other religious traditions, there are a number of deities involved. In the Chinese tradition, there's an entity that cracks open the great egg of the universe. The Aboriginals have their own tradition. The Maidu people of San Diego have the legend of the great turtle who brings up earth from under the sea and starts to create the planet out of this red clay and humans and so on. But divine entities are involved in many of these stories. Others argue it was born from absolutely nothing. In fact, Fan Ku, the Chinese creator of the universe, creates this thing out of absolutely nothing, although, as I say, there is an egg involved. So where the egg came from is another story. I'm not too sure about some of the ambiguities there. Or is the universe eternal? For the ancient Greeks, all that existed was eternal chaos, and the gods were able to bestow logic, logos, right? Which also is the word for the word in classical Greek. So logos, logic, in the beginning was logic, in the beginning was the word, derives from the classical Greek story. But the argument is that this seething mass of energy was eternal, and then logic was bestowed upon it. All these creation stories have to face this paradox, right? How can something come from nothing? If something created everything, where did the something come from? Where did the gods come from? If God is eternal, or if anything is eternal, how is eternity made? How do we conceive of eternity? Was there ever a beginning to eternity? Or is that a ridiculous paradox, even to suggest that? Can any creation story solve these conundrums? The only one that thinks it can, and it does so tentatively, and it's worked this out over the last really 40 or 50 years in any sort of detail, is the Big Bang Theory, coming out of modern quantum physics, which argues, as bizarre as this seems, I mean, what a bizarre creation story this is. Everything that's ever existed in the universe was created by a tiny subatomic sized particle that popped into existence out of where we have no idea about 13.7 billion years ago. And everything that's existed since then has come from that particle. Now, why on earth would most physicists on this planet, the overwhelming majority, believe such a bizarre story, right? The answer must be that there is evidence for it. And at heart, this is a history course. As historians, we deal with evidence all the time. And even though I'm not at all supremely qualified to discuss the evidence of quantum physics, I think I've read enough about it to at least give you an outline of what this evidence is. The theory emerges from attempts not to discover the origins of the universe at all, but to try and map the cosmos, to try and position stars, to try and use parallax to measure how a star seems to move in relation to some backdrop of the galaxy behind it and so on. Parallax using trigonometry and so on, and observing the position of a star against the backdrop in, say, the autumn and then again in the spring, can give you some sense of how far away that star might be. A particular American astronomer, a female astronomer, Henrietta Leavitt, back in the early 20th century, started focusing on a particular group of stars, Cepheid variable stars, that sort of pulsed light quite brightly at a regular interval, and this was very helpful in allowing her to get a decent fix on this star and also start to measure distances. Then the idea was evolved that we could use spectrometers. We could examine the light coming from stars, put it through a prism and a spectrometer, and see which end of the sort of almost barcode that emerges out of a spectrometer the light was shifting to. Light, like other waves, like sound waves, will squash up as it's coming towards you. Think about how a siren and an ambulance siren or whatever will get higher pitched and almost faster as it comes towards you, then immediately stretch out and slow down as it goes away from you. The sound waves get squashed up as it approaches, stretched out as it moves away from you. Same thing with light. It was discovered. And if all the light was shifting to the red end of the spectrum, that suggested that every piece of light these astronomers were looking at was moving away from the observer at a very fast rate. Edwin Hubble, and if you've ever wondered why the Hubble Space Telescope is named Hubble, this is the reason, because this man is largely responsible for the beginning of the Big Bang Theory. Hubble was looking at galaxies from the Mount Wilson, I think, observatory in Los Angeles, now largely useless because of light pollution there, of course, in the whole Los Angeles basin. But he was noticing wherever he looked, except at the very closest galaxies to Earth, everything was redshifting. And the further out he was able to look, the faster they seemed to be flying away from him and apparently from everything else. Which means he comes to the extraordinary conclusion, this universe is expanding. Wherever I look, I'm seeing rapid expansion going Living in Los Angeles, he started to think like a cinema photographer. What if I could freeze this shot and reverse it? Does this mean, as bizarre as this sounds, that the universe was once very, very small, and for whatever reason it started to inflate and has been expanding ever since? This bizarre idea, he even came up with a mathematical formula for measuring the rate of expansion, which was not particularly accurate at the time. But this bizarre idea was sort of published in a few journals and didn't really take off for a couple of decades. But it remains the fundamental piece of evidence for the Big Bang. Very brief overview of what the theory says. Before 13.7 billion years ago, we can say nothing. We have no idea what existed before this moment. Hawking and others sort of can prove that as you get closer and closer to that point, calculations just go crazy. They wrap back up around themselves and so on. Did space and time not exist before this entity pops into existence? Are there parent universes out there and various other universes, parallel universes, keep somehow dropping out of this parent universe? No idea. Did this happen in a black hole? What's the role of dark matter and dark energy in all of this? No idea. Incredible speculation going on out there, but no clear idea. All right? So we can say nothing before that. For my students, many of whom are profoundly religious, that's actually comforting. They see a role for God right there. They say, well, clearly this is the egg that God put in place to create the universe. I don't dissuade them of that view. I just say, well, if that works for you, that's fine. So this thing appears 13.7 billion years ago, incredibly hot, unimaginably hot temperatures. Although some of these have been replicated now in various laboratories and particle splitting devices and so on. So we don't know what there was before the spec or why it appeared. We cannot answer these questions yet. Then we've got a series of events take place just in the first few split seconds. We've got cosmic inflation creating this, so sort of rapid inflation of this entity, creating this large patch of space that's full of some of the building blocks of what will become atoms later, quarks and so on. Lumpy, not very diffuse initially. These forces appear early on as well, forces that we're all very familiar with. I've got some simple analogies there. I mean, you can prove gravity every time you fall off a mountain or drop a pen, obviously. The electromagnetic force, a strong force that has a role in gluing neutrons and protons together to make atoms and so on. Weak force would seem to have something to do with radioactive decay. Stephen Weinberg has theorized another force, almost like the fifth force, quintessence force. But it looks like those forces appeared in this very early moment. There's then, again, sounds like something out of Star Wars, an extraordinary conflict or battle between matter and antimatter. And there are wonderful books out there on why there must have been a little more matter than antimatter, and why matter wins out of this sort of cataclysmic context, if you like, contest. And then eventually protons and neutrons start to form from these quarks. Then this annihilation continues, and then massive inflation, massive releases of energy. And the Big Bang, literally. So I turned that up louder. I forgot that was coming. Where there had been virtually nothing, now there's this tiny universe. It is a complete universe, but very, very small compared to today's universe. In an instant, it expanded. And now, I'm saying faster than the speed of light, which should be impossible. But I've read a number of physicists and a number of their accounts that suggest inflation may well have happened faster than the speed of light, although that's contentious still. So this extraordinary inflation. And then the initial inflation begins to slow just a little bit, right? But the universe keeps on expanding as it still is today, although the rate of expansion, well, is it slowing? Is it constant? Is it even speeding up? That's something we'll come back to in our very final gathering. The next critical date in the history of everything, essentially, in this modern account of origins, is about 380,000 years later, a date that particle physicists have given us with some accuracy, they think. It would have taken about 380,000 years of this rapid inflation, even slowing inflation, for temperatures to drop enough so that nuclei, right, and of what will become atoms, and electrons no longer have enough energy to resist the electromagnetic force. These atoms begin to glue together. The first stable atoms form, releasing a huge amount of energy again. I've read other accounts which suggest some sort of light must have flooded through the universe for the first time at this point. So it's like a very thick, foggy soup, but as these atoms form, the fog clears, energy and light flows freely, releasing a huge amount of cosmic microwave radiation. That's important to the account and particularly important to the evidence. Gravity then continues to amplify small differences in the density of these gases that are created. These first stable atoms create the two simplest elements we're aware of. Hydrogen, helium, maybe a tiny bit of lithium as well, right? The simplest combinations of protons and neutrons. But this gas is not diffused completely evenly. There are sufficient pockets of density, right, for gravity to begin to work on, to begin to compress some of these clouds. Is this an incredible story? It's an amazing story. Okay, so some mathematicians and quantum physicists like Gamow, Alpha, and Herman, and so on, in the late 1940s start to think about Hubble's findings and start to almost theoretically speculate that this huge release of radiation at that point, perhaps 380,000 years after the Big Bang, should have left so much energy that it should be detectable today. And they even begin to prophesy what sort of temperatures you can see there this radiation might be at. I haven't got time to go through the whole story of Penzias and Wilson and the pigeons, but Penzias and Wilson were building extraordinary radio telescope type device. They were getting a lot of interference. This is in the 60s. Wherever they turn their antenna, they're getting terrible hisses and so on. They thought it was the pigeons that were roosting all over it. They took the pigeons to the Midwest somewhere. They were homing pigeons. They came back to New Jersey. In the end, they killed the pigeons, poisoned the pigeons. Still, this hiss, wherever they turn this thing, this hiss is coming. And physicists hear about this discovery and suggest what you may have found here is this echo of cosmic background radiation. These two guys, with this almost accidental discovery, end up getting the Nobel Prize for Physics. Particle physicists have been working with a lot of these ideas about what would temperatures have been like in conditions in the very early seconds of the Big Bang. They try and replicate these conditions. They try and smash apart atoms at very high temperatures, very high speeds, and so on. They began to predict early on that the universe would probably be made up mostly of 25% helium and 75% hydrogen, a little bit of lithium, and this is leaving out of the whole story the question of dark energy and dark matter, which we really can't go into tonight, which is another huge issue. But these estimates of the gases were exactly what was found when we started sending up space probes and measuring and so on. So this evidence has been sufficient to convince physicists of every culture, of every religious faith and so on, of every language, that the Big Bang is the best origin story we have available at the moment. Right? And I've given you a very, very quick overview, and I apologize about that. Is it true? Right? And how can we say that with any certainty? Absolute certainty, totally unattainable. And this story, some parts of it already are being tested and pushed by quantum physicists. And you only have to subscribe to Scientific American or read Science Magazine or others of that ilk to get some sense of the incredible thinking that's always going on with this theory. But it has consensus. It has not been falsified. These are the two critical tests for most scientific theories. It fits a vast amount of data. In fact, if there's one unifying feature with all these theories, it's the amount of data from these different disciplines that fit into these major paradigms. And as I say, unlike all earlier creation stories, this is the first creation story we've had that's accepted globally, right, by people of every faith, every culture, and so on. So this is the best story we have at the moment, I think. But I would never dare to suggest it won't change dramatically in the future. Have a quick drink. Excuse me. So we know the early universe was simple. Right? Now we're moving more into the realm of astronomy, but obviously quantum physics plays a huge role here as well. And one of the themes that begins to emerge in this sort of cosmic history, it's a simple theme, right? And also we'll see when humans appear on the scene is simplicity seems to evolve to complexity, right? At almost all scales, all levels. So the early universe, very simple. We have some basic gases. We've got some very significant forces involved, particularly gravity. But gradually more complex entities appear. Just do some Google image search. You'll find all sorts of extraordinary attempts by artists to render some visual view of what this must have looked like. The dawn of time, or at the beginning of everything, this expanding universe, early stars lighting up, early galaxies, much larger galaxies, expansion continuing, and so on. There are many, many wonderful images online like that. So increasing complexity becomes a significant theme of big history. And the first complex thing to appear, really, after the Big Bang are stars and galaxies. Okay? So we know, again, in the early universe, there's this huge amount of radiation. We know that gravity is very significant already. There's these huge clouds. Again, artists' impressions. A lot of Hubble images also. I'll show you a couple tonight. But just search for any theme here through the NASA side or through the Hubble Space Telescope side to get often coloured and rendered images of what Hubble is discovering out there almost every day. So huge clouds of these two basic gases. And that's all you seem to need is gravity, hydrogen, and helium to create everything else that's being created in the universe. Right? Simple recipe for stars. Gravity, hydrogen, and helium. So gravity, you can imagine, is working to compress these slight differences in temperature and density of this gas. As it crushes and compresses these gases, temperatures increase. Simple analogy like pumping up air in a tyre. Pressure is increasing, they're getting hotter at the same time. So we've got these huge piles of atoms being pulled together into these vast clouds, getting more and more compressed all the time. This process continues not very long and is still going on today. Again, Hubble has got these extraordinary images of great clouds that are almost like star nurseries, where gravity is crushing, compressing, increasing pressure, increasing temperature, so that stars actually begin to light up inside these vast clouds of gas. That's the Cone Nebula. The previous one in the backdrop there, I can't read what that was, but do the search for yourself. It looks like the temperature that's critical here is about 10 million degrees Celsius. So when this pressure creates that temperature, essentially these clouds of atoms begin to turn into extraordinary fusion bombs. Hydrogen atoms at that temperature begin to fuse to form helium. Right? You've got two hydrogen atoms coming together to form helium. This releases a huge amount of energy. We know about this from fusion reactors, from fusion weapons, and so on as well. This energy that's released now through this fusion process stops the gas clouds from collapsing anymore. Think about our sun up here now as a huge gas cloud with this extraordinary release of energy going on inside where this fusion is taking place. Gravity's still trying to compress it, but these two forces are somehow held in bay, right? And these stars are essentially stabilized by these two conflicting forces. So at 10 million degrees Celsius, give or take, hydrogen atoms begin to fuse together with the power of millions of... hydrogen bombs is a simple analogy, but you're getting the sense of the same sort of processes we've been able to replicate here on Earth. For a while, we thought that the first stars did not form for perhaps 2 or 3 billion years after the Big Bang. It now looks like, again, with evidence from the Hubble Space Telescope, that stars were formed quite early. Within 200 million years of the Big Bang, the first stars and galaxies were formed. These stars cluster together in huge galaxies because the galaxies are the same cloud from which these individual stars have been born from. And each one of them, our own Milky Way, for example, they contain hundreds of billions of new stars. So why does all this matter? Why do stars matter? Do you remember the old Joni Mitchell song, Woodstock? We are stardust, we are golden, we are billion-year-old carbon. I don't know if you remember that. It's a song I used to sing a lot back in the 70s. I love that song. None of my students have ever heard of it, or Joni Mitchell. Who? Woodstock? What's that? So a brief summary. These stars really do have a life history. Every star does. I'm almost embarrassed again by how simplistic this is, folks. We'd spend a couple of weeks on this. We'd look at all the different scales of star sizes and how that affects their rate of growth and so on. But essentially, every star begins as a huge cloud of gas and matter. These are all observations that have come to us from the Hubble telescope. That's the Orion Nebula. The cloud collapses, as I've suggested, under intense pressure from gravity until a star is formed. It might shine for at least hundreds of millions or maybe many, many, many billions of years, depending on the size. Essentially, small stars live long, boring lives. They live a long time. Big stars, think James Dean. Big stars live this wild, frantic life and burn out very quickly. So the size is critical. Eventually, stars die, right? Essentially, they run out of gas. If they're big enough, and that when they die, it will be in a cataclysmic death of a massive explosion, a supernova. What's important here is that these dying stars create all the more complex elements that exist in the universe. Remember, the only elements that were created in the beginning were hydrogen and helium. Where does everything else come from? Including carbon and gold and whatever, every element you can imagine. They're essentially created in the death of stars, by the death of stars. Stars run out of gas, as I said, literally. They start running out of hydrogen. As their centers cool, they start to collapse. This raises pressure, raises density. Temperatures increase again. It's sort of increasingly frenetic almost, temperatures may reach 100 million degrees Celsius, at which point helium starts to fuse to form more complex elements. When they start running out of helium, helium atoms, a whole sort of cycle of higher level fusions of elements takes place at higher and higher temperatures, until in very large stars, a series of collapses forges elements like oxygen, like carbon, nitrogen, everything up to iron, number 26 on the periodic table. Here's a table you may have memorized when you're at school. Did you have to memorize this, any of you at school? I bet some of you did, yeah. Everything up to number 26 there can be created by the death of a sort of medium-large star, right? In this sort of vast cooking process, if you like. Where do all the other elements come from then, right? That's a big question. In the death of giant stars, supernova. They explode so violently that for just a few days they can outshine an entire galaxy. And we've observed a number of these now, both here on Earth, like the Star of Bethlehem was most probably a supernova, and many, many more now with our sophisticated space telescopes and so on. In just a few seconds of this cataclysmic finale of its life, all the other elements of the periodic table are cooked up and then sort of scattered through that immediate neighborhood of the universe. There was clearly a supernova close to the region in which our solar system formed, which is why when our planets formed, there are a lot of other elements involved instead of just those two gases that we mentioned earlier. All right? Again, just good fortune, Goldilocks again. Here we are with, well, it's just a fact. I mean, I'm not making any claims except it's just a fact. So everything else is cooked up here. Recently, a hypernova event was observed by some Australian astronomers. This is a star that was so massive in its cataclysmic finish that in a few seconds it would have produced more energy than our sun will produce in 9 billion years. And it was way off on the farthest reaches of our... actually, I'm not sure where it was exactly. I'm trying to think where it was located. But physicists already speculate what other elements may have been cooked up in these enormous temperatures. What other elements might be capable of being created by these vast star deaths? And we don't know. We may never know. So we literally are stardust, is where that Joni Mitchell song comes back into it. Stars make the materials of our world, and for all of this vast origin of this story, this is a story that focuses very much on our world, as I hope to show you. All these materials, that's just a handful of the materials that were made, and the materials for carbon-based life forms such as gerbils, such as any life form you want to imagine here on this planet. So moving on, how are we going? We're going very well, exactly halfway through. The third topic is how do you create a solar system then? We see, at the end of this, by the way, there will be a test on these major theories and the evidence for them. So I'm sure you're keeping up. So you might make notes, so that's a good idea. But again, this is just to make you aware of these theories and their significance, and not to suggest in any way that this could replace a detailed, in-depth scientific course. Right? But it's important, I think, that every educated human has some grasp of this, just as every educated human should have some grasp of Beethoven's symphonies or the great poetry of the Tang Dynasty or Shakespeare or whatever, or how to dance or everything else. So, to me, this is part of what makes an educated human being, at least having some handle on this, some grasp of this. So it now looks as though, right, that the sun absorbed about 99% of the original cloud of this material that was available in this particular neighborhood of the universe, if you like. So as gravity starts to work on this cloud, which includes the basic elements we discussed of hydrogen and helium, but now all this other stuff, all these other more complex elements, the sun actually absorbs the great majority of it into itself. Right? The other 0.1% was in the form of a solar nebula, a solar cloud, which, if you can imagine, is sort of orbiting around this embryonic star in the center here, right? As a huge cloud of dust, other debris, ice, frozen gases, and other elements. It begins to orbit. It flattens out through the orbiting process, flattens out in sort of a pancake shape, if you like, and it's orbiting the sun in a series of rings. The rings of Saturn give you some idea of what this may have looked like early on. Some idea, although I don't want to make that analogy too precise. As I mentioned, this nebula, this cloud, contains gases, dust, ice, and so on. The sort of stuff that we do detect in comet tails today, by the way, sort of material. And it's these leftovers, these bits that are just stuck in this cloud around the sun, that will eventually go on to make the planets and other objects in the solar system. The process that's involved here is accretion. So imagine these bits of rocks and minerals and frozen gas smashing into each other in these chaotic orbits around the sun, right? Extreme violence. And they stick together because of gravity. A larger chunk will be hit by a smaller chunk. It might bounce a bit, but gravity will pull it back in together again. And you'll start getting larger chunks of this debris, this material. Once they reach a particular size, between 10 and 100 kilometers in diameter, astronomers give them a name, planetesimals. Right? So imagine this huge cloud is now starting to shape itself into a number of larger objects in here that, as I say, astronomers call planetesimals. They grow in a sense like snowballs, another simple analogy, but it helps particularly my students. And as they get larger, their gravitational pull is increasing, of course. They're attracting more and more stuff. Smaller planetesimals hit large ones and stick to them because of gravity. And eventually, when they reach this size, an object between 100 and 1,000 kilometers in diameter, they become a protoplanet. You can read this in any standard astronomy textbooks. Absolutely fascinating. Eventually, in each orbit, one large protoplanet absorbs most of the other material, right? So you end up with a series of concentric orbiting protoplanets. And as they get larger and larger, you end up with planets. Once they're more than 1,000 kilometers in diameter, one to each orbit. There may have been 40 or so planets late in this process that coalesce down to the handful of planets that we have today, through collision, through gravitational attraction, and so on. Now, there are some astronomers that dispute this, that this is the standard paradigm of how solar systems form. As we start to acquire more information about other planets out there that appear to be in orbit around their suns, there is some evidence suggesting this model does not always hold true. And of course, you'd expect that from specialist astronomers to be constantly testing this theory and trying to advance it somehow. And so we end up with this. Now, all these large objects have absorbed all the material in their own concentric orbits, if you like, and have, for a long time, as you know, meteorite collisions and so on, asteroid collisions continue with these entities, but eventually the rate of these collisions slows down as more and more of this material is absorbed into these planets. You can see this a little out of date because poor old Pluto, who recently lost his position as a planet, for a number of reasons, doesn't quite fit the model, seems too small, can't prove necessarily it was made from the same accretion cloud. So Pluto's still here, but imagine how Pluto was gone. If this was to scale, Pluto would be somewhere way beyond Robinson Road out there, if this was really to scale. But I didn't have a screen, no screen big enough to do that, unfortunately. Okay, so what about the early Earth, right? The image of the moon there. But looking at the surface of the moon, we get some sense of the violence on this early planet. These constant collisions, incredible temperatures, massive volcanic activity continuing. We can see the scars on the moon because it doesn't have an atmosphere, it doesn't have erosion the way we do on this planet, which has covered up these scars on our planet through erosion and of course, vegetation and oceans and so on. So the early Earth, we're talking about 4.55 billion years ago, extremely hot, much hotter than today. Violent collisions are continuing, as I say, very high internal radioactivity still. Pressure, it's still growing, it's being crushed still by gravity. Eventually it gets so hot, again, apologies for the rapid general nature of this account, but it gets so hot that it begins to almost liquefy, or at least turn into a sort of a molten sludge, in which all of the random elements that have been brought together to create this thing, right? Bits of iron here and nickel and all the other elements that are here begin to sort themselves out under extreme temperatures. The heavier metals begin to sink towards the core. So we end up with a hot iron nickel core. Lighter elements will form mantles. Lighter elements, again, volcanic rock will cool and form crusts. The lightest elements of all, the gases, will come out of these incredible volcanoes. And once the Earth is large enough to have a strong enough gravitational field, these gases will be trapped to form the Earth's first atmosphere. Right? So the Earth acquires a structure. Look at any National Geographic cutaway of the Earth, you'll see the whole thing. How do we know what's inside the Earth? No one's ever dug down more than a couple of miles, not even that, maybe as far as I'm aware. We use all the different waves that seismographs measure all the time. We know what materials waves will pass through and won't pass through. We have seismographic listening stations all over the planet. It's seismographers studying earthquakes and so on that have been able to put together this model of what the early Earth, the center of the Earth probably looks like. Now, there have been changes, of course. This is terrible. One slide on the most important paradigm of Earth science, and I really apologise. Any geologists in the room, you can take me out and slap me around later. Sorry. I'm sorry. Things do stabilise, right? The Earth cools, there's less collisions and so on. Eventually, all this water vapour that had been stored in the atmosphere, as cooling reaches a certain level, begins to rain down in thunderstorms that must have lasted for millions of years. And all this liquid runs across the surface and fills up the various hollows and crannies and so on. Right? The seas were formed. Meteorites, as I mentioned, arriving less frequently. Undersea volcanoes. This is something that was only discovered after the Second World War. Back in, I think, 1916, a German climate specialist, Alfred Wegener, just looking at a map of the Earth, said, this looks like a giant jigsaw. This looks like this part must have fitted in there, and these parts must have fitted. But he was a scientist, and it wasn't just the look of the thing. He was able to study mountain ranges and certain folds and faulting and so on that seemed to leave off here on the west coast of Africa and then to be picked up on the Atlantic coast of South America. Precisely the same angles of inclines and synclines, precisely the same rocks. He was able to find lines that seemed to go from sort of North Carolina through Greenland into Scandinavia, lines of geological features. And he argued, as bizarrely as it sounded, that he believed the continents were moving across the planet. And as a German, he announced this in the middle of the First World War at the American Society of Petroleum Geologists meeting, and it didn't go over very well. Basically, they said, no, you're wrong. And so he said, well, how can we find very similar animals living in? So then there were theories about huge land bridges. Can you imagine this? There must have been massive land bridges that connected these continents. That's how animals were able to move back and forward and so on. And Wegener, frankly, could not explain what forces could possibly force these big chunks of continent to move. Only after the Second World War, using sonar to map the seafloor, were these huge chains of undersea volcanoes discovered. And when samples were taken up from alongside these chains of volcanoes, it became obvious that new crust was being created, that the crust was sort of being forced apart beside these great chains of volcanoes. Also, coincidentally, and not critical of the story, they found out that the polarity of the Earth had changed many times over the last several million years. That is, the first band of rocks beside the volcanoes seemed to be all of those minerals and the rocks that were attracted to the north were being pulled to the north, were aligned towards the north. Go out a couple of hundred miles, everything seemed to be pointing to the south. Go out again, they were pointing to the north again. And again, as bizarre as it sounds, it looks like the north and south poles, in terms of their attraction, have flipped a number of times. Geologists that I read and geologists at my university say we're actually long overdue for another flipping of the poles. But no one can speculate what that might mean, frankly, to our lives. Or to anyway, so new crust has been created here. Does this mean the Earth is getting larger? No. In other areas, we're aware of other crusts being sucked back down again, as oceanic and continental crust can ride over each other. But this is forcing continents apart. And now, of course, we use GPS satellite positioning to be able to prove absolutely, in relation to satellites, that Australia is moving north at about 4 centimetres a year. I jokingly said last week that Australia will be off the coast of California. That seems absolutely inevitable. None of us will live to see that, but and we now know through plate tectonics, this extraordinary paradigm of plate tectonics, that the surface of the Earth has looked very, very different over the last millions and billions of years. Plate tectonics becomes the core paradigm of modern Earth science. Again, like the Big Bang, it seems to account for so much data. Like evolution by natural selection, it accounts for so much data. Just a couple of examples. It tells us a lot about mountain building, volcanoes and earthquakes, why the continents are where they are at the moment, the whole shape of the modern world. This is important for human history. What if humans had appeared on a planet in which all the continents were connected? It's actually the isolation of humans in North America, as we'll see next week, that allows us to get an incredible glimpse into historical processes, because we can observe, once humans migrate to the Americas during the last ice age, when there was a land bridge here, and also perhaps using canoes, eventually after sea levels rise, humans are sealed off here. So we're able to observe parallel historical processes in the Americas and Afro-Eurasia, and look at very interesting similarities and differences in the way these histories evolve. If humans had appeared when all the continents were together, we wouldn't have these separations, these isolations, these different world zones that are so important. There's Pangaea, a mere 180 million years ago. All the continents joined together. The dinosaurs are able to roam freely as far as they can adapt to different environments, from near the South Pole to the North Pole, from North America, which I think is number 7, through to Europe and so on. Things begin to break up 120 million years ago. This is the Cretaceous period when the first flowering plants and marsupials and so on appear. You start seeing North America's shape becoming very clear there. Clearly Africa and South America joined, so animals moving freely back and forth there, and plants as well. Starting to look more like the planet we recognise today. This is just a mere 60 million years ago, when the Cretaceous asteroid impact slams into most probably the Yucatan Peninsula, and so changes the Earth's climate that the dinosaurs die out. Oh, that was the impact. Let's hear that again. Thank you. I forgot those sound effects are there. India, you can see, is a separate subcontinent driving towards the Asian plate. Look at it driving up there. And you know what it's going to form when it smashes into Asia? Right? The mightiest mountains on Earth, the Himalayas, which I had the pleasure of visiting in October last year. And to see this incredible sort of upthrust. Mountaineers were absolutely astonished when they started finding marine fossils on the summit of the highest mountains on Earth. Said, how the heck can these fish have got here? Of course, a lot of theologians said it's the Great Flood. And I don't want to dispute that, but a lot of physicists say that if the water was that high in the planet, we would have been thrown completely off orbit and long ago have disappeared as an entity, this planet, if there had been that much water to be as high as the Himalayas. Oh, collision again. So I've now got 15 minutes to cover the entire history of life science. And I know there's a biologist in the room. I apologise. So we've looked at the core idea of modern astronomy. I think now you're all pretty clear on the universe, how it was formed, and what the evidence is that supports that, right? Fairly clear on modern science, I hope, including an embarrassingly fast romp through plate tectonics. Now, we have to conclude this scientific part of the course. I hate saying it that way because really the way this course is taught, the way the story unfolds, we attempt to make not a sharp division in the course between the science component and the sort of human history component. Inevitably, with 4 lectures, it just made sense to do it that way. But it's not quite that sharply defined in a regular course. Explaining life, here's the biggest challenge of all, perhaps. This is my last topic for tonight. Now, when say to your students, what distinguishes something that's living from something that's non-living? What distinguishes you folks from the chairs you're sitting on? Biologists are able to offer us, I think, and again, this is fairly simplistic, but 3 clear criteria that all living organisms share. Right? Certainly they've got the ability to adapt in some way to find new ways of extracting energy from what has clearly been a changing environment. Right? We've seen, imagine how much the environment of the planet has changed over the last 4.5 billion years. All living things can preserve these adaptations by replicating them somehow through reproduction. So these changes, which, as we'll discuss in a moment, if these changes are beneficial to a species in a changing environment, there has to be some way of preserving these adaptations, right, through replication. And every living thing finds the energy needed to support itself somehow, right, to support these complex adaptations. This is as true of a bacteria as it is of a stonefish on the Great Barrier Reef or a human or a camel or whatever. Every living entity seems to share these 3 criteria, features. So, to sum that up, right, adaptation that's preserved by reproduction and is powered by metabolism, or acquiring energy, explains, frankly, why this little fellow is so much more extraordinarily complex than the vast sun that's sustaining us all up there, which has got a simple core radiation zone and convection zone. It's a very simple entity. Right? And look at the complexity of that of the fly. Life clearly introduces a whole new level of complexity, at least on our planet. It looks like in our solar system, and who knows how much further afield this applies. Now, the problem has been, how do we explain adaptation in particular? We can see we've got all sorts of examples of how metabolism takes place and so on. We can see reproduction, but how do living organisms adapt to their environment? Right? The central challenge of modern biology. Human eye, extraordinarily adapted for seeing. Sending messages to the back of the brain and so on, which we translate into messages that we understand and act upon. How did it get that way? The eye is often chosen by creationists and intelligent design proponents to say it's not conceivable that something this exquisitely adapted could have come about through random processes. Biology would disagree. And so evolutionary biology would say, absolutely, this is as much a product of random adaptations as anything else that's existing. Traditional answers, of course. Carl Linnaeus, a very intelligent man, founded the whole approach of taxonomy, where we classify species and so on according to genus and family. He said, life is fixed. God made creatures already adapted. God made us with these eyes. We have not changed since. Right? Linnaeus is someone certainly worth reading. This is the traditional answer. Animals are well adapted to this environment because they're designed by a benign creator. Right? And for many people, that is a sufficient explanation. But there are problems with this theory, particularly for scientists. One problem, all these fossils. I love to, we use some readings with my students from Charles Lyell, early English geologist, almost the father of geology. And Lyell and his colleagues are on the White Cliffs of southern England with their hammers, chipping out bits and finding these extraordinary fossils, trilobites and other creatures that clearly don't exist anymore. And if you can measure the number of strata down they haven't existed for a very, very long time. Just a few examples you can see there. Of course, this was the whole theory behind the, what was the movie about dinosaurs being recreated by Jurassic Park, right? That DNA is preserved in amber, dinosaur DNA, and that you can recreate these creatures through their DNA. None of these species exist today. So what does that mean? Right? Also, breeders know that living organisms can change all the time. All modern breeds of dogs are descended from wolves. I'd love to spend time to discuss the various theories out there about how the wolf becomes domesticated by early humans. Essentially, does the wolf self-select by certain members of the wolf species following Paleolithic migrating human groups, living off their trash and so on? Or do humans carefully select individual wolves that seem more malleable, more of a herd instinct, more useful, tamer, whatever? But breeders know that. Australia's early success as a wool exporting nation was on the back of a particular type of sheep called the merino ram, merino. And it was an English sheep breeder, John MacArthur, who bred various types of sheep to literally create this sheep designed for the harsh Australian environment. All the English sheep that came out died very quickly straight away. So he said, I'm going to make a sheep that can survive here in Australia. So, we've known about artificial selection and breeding for a very long time. Right? It's Darwin who comes up with explaining how species adapt in the natural world. We know how humans can interfere with these cycles and create something new. How does this happen naturally? And that was Charles Darwin's extraordinary gift to all of us. He's quite a young man when he got a job on the Beagle, spent a couple, 4 years on an incredible, 2.5, I can't remember, incredible voyage around the world. That job should have gone to Joseph Banks, who was the great naturalist of England at this time. He had sailed with Captain Cook to Australia, by the way. Banks had been the first to sketch kangaroos and the platypus, and in Australia, every city has a suburb now called Banksia. There's banks everywhere. Various trees are named after Banks. Banks was now far too famous and a little old. He said, I'm not going to go on another darn voyage around the world. So young Darwin got the job, right? And 20 years later, after pondering this, after being so horrified by the ramifications of what he's discovered, he almost reluctantly publishes The Origin of Species by Natural Selection in 1859. Fully aware of how this is going to outrage a lot of people. Now, Darwin saw lots of things. Again, apologies to biologists. Here's just one thing he saw that really intrigued him. They visited the Galapagos Islands, wonderful volcanic islands off the coast of Ecuador, I think. I think Ecuador owns them today. And he observed that these islands were close, but a little too far apart for the small birds to fly between them. He visited 14 different islands and found 14 identical species of finches. Clearly, he thought the same species, but all with different beaks, different head shapes, and so on. He said, clearly, somehow, each one of these birds is really well suited to this particular island environment, right? Is this some form of adaptation? The puzzle was, and as he did a careful study of the botany of these islands, each island had a different type of tree or different types of vegetation. The beaks were perfectly adapted to the specific trees, nuts, fruits, and so on each island, right? Each species had somehow, he didn't know how, had somehow made tiny adaptations to their own local environment. This one's got a particularly hard, solid jaw to chew into this very tough cactus, for example, right? So Darwin is deeply pondering this. And he's thinking, have I caught natural adaptation, if you like, going on? Have I caught it somehow in the act? Am I looking at what will eventually be the creation of 14 new species? that will become so different in the end they'll no longer be able to mate with each other. And he believed that that's what he'd seen. He thought that these tiny variations between these individual finches were magnified when some geographical barrier, and in this case it was the ocean. He was also aware of discoveries of squirrels either side of the Grand Canyon, grey squirrels here, black squirrels there, and so on, appear to be the same species but quite different adaptations. Right? Somehow a geographical barrier had stopped individuals of the same species from mating. Right? So as I say, he thinks he's caught the creation of several new species. They become more and more different from each other, diverge more and more. Eventually, when groups can no longer interbreed, they form a new species, right? And this becomes his core idea, evolution by natural selection. Nature is selecting individuals that will survive and prosper by the environment. Let me just explore that a little bit more. The environment's constantly changing. So what makes a particular individual bird, for example, best fitted to an environment will also keep changing, right? So the definition of survival of the fittest will keep changing. It's nothing to do with your strength necessarily. Natural selection then is this endless process. As the environment's changing, species are making tiny adaptations. Individuals within this particular species, for example, might be born with some genetic mutation which happens to give them an advantage in that environment, right? Other adaptations that people are being born with might be disadvantageous. The individual that's born with an advantageous, whatever it is, trait, is most likely able to get more food, have more mate more often, pass this trait eventually on his offspring, his or her offspring, so that over time this trait will spread through the population. Never ending, and if Darwin had got it right, he thought this explains this extraordinary variety of organisms. Right? We've all come from some original core entity, and through these adaptations to different environments and these divergences, we've ended up with this massive biodiversity. Billions and billions of different species on our planet. Now, again, very, very simple, and I apologise for the simplicity of that, but the ramifications were obvious for Darwin. He comes from a strong Christian family. His wife was profoundly Christian, father a minister. And what he's saying was, right, so blind processes are creating these complex things. Blind, statistical, random processes, right? All living creatures are probably related. We all come from the same ancestor, this means. You can see why he locks this thing away in his drawer for 20 years and doesn't want to publish it. And humans are closely related to apes. He guesses. He says we seem most closely related at this time. We seem to share quite a lot of traits and so on. So we must have shared a common ancestor quite recently in biological terms. One of the reasons he didn't publish, apart from the Christian problem, is that Charles Lyell, his geologist friend, was saying the Earth might be at best a few 100 million years old. Darwin was saying that's nowhere near long enough for these processes. I need hundreds of millions or billions of years for this to happen. And so there was an example of a theory that was falsified by the information at the time, right? By the theoretical or the age of the Earth as it was understood by geologists at that time. What evidence did Darwin have? Well, fossils, all sorts of fossils he looked at. The Archaeopteryx you've probably seen looks like half reptile, half bird. He amassed a massive fossil collection. He believed he'd found fossils of animals and other species in the process of changing from this to that. Again, if I had time, I'd be showing you many examples. He looks at different species in their embryonic form, homology, under the skin. He sees very, very similar shapes, controlling mechanism, a spine, often sort of finger bones, even in a porpoise's flipper or other entities that suggest all these creatures once came from a common ancestor. And he sees different types of species that make similar adaptations to a specific environment. He sees completely different species in Australia that have nonetheless come to resemble each other as they've all had to adapt in a similar way to a particular environmental niche. And since Darwin's time, we now see evolution at work all the time. There are scientists out there who love to play with the fruit fly, who love to pump different gases, change its environment, see this thing change almost before their eyes into something different. I mean, micro changes. Of course, HIV and other viruses prove that if we change the environment through inventing a new retrovirus or a retro drug of some sort, the HIV can very quickly adapt to the new environment that we've created with these drugs. Same is true of other terrifying viruses that you find in hospitals today and so on. Of course, with Crick and Watson's work back in the 50s, we've now got a very clear idea of how DNA works, and I'd love to spend time discussing that with you, but unfortunately we won't have the time. And now the incredible discoveries of of genetic mapping, Human Genome Project, and so on, we can prove that all these living organisms are related and go back to a common ancestor. I'll just throw this out there for you. This is what I heard from some colleagues at University of Michigan recently that are involved in mitochondrial DNA. They've tested, I think, something like 500,000 women now, and I think I mentioned this last week. And I believe absolutely that this proves that every woman alive today is descended from one common ancestor, from one mother, who they call Eve for obvious reasons. But they believe there were more human mothers in the original small population of humans, but the other lineages have died out. So, I mean, gene mapping and so on now is just every day offering more and more evidence to support this theory. Is that enough evidence? Clearly not for a lot of people. Right? There's a lot of people who will not accept that. It's the core idea of modern biology. Gosh, I'm going to have to move quick. This is as fundamental as Big Bang cosmology and plate tectonics, right? Last question. I'll do it in 5 minutes, and this is embarrassing. 5 minutes. How does life appear on this lifeless rock? Right? I mean, this seems, think of all the other theories that are out there that life's brought here by asteroids. Of course, God put us here. I mean, there's all sorts of other accounts. The current three-stage theory of chemical evolution theory, right? The Earth manufactured simple organic molecules, amino acids, nucleotides, phospholipids, and so on. These turned into organic chemicals through chemical evolution that evolved and started to behave a little bit like living organisms. They began to metabolize. They began to reproduce in a fashion, right? And then DNA eventually emerges much, much later. We have RNA for a long time. DNA emerges to control replication. That's the theory in a nutshell. Let me expand just a little bit. Now, Harold Urey and Stanley Miller set out to try and prove this bizarre idea. They created this incredible series of retorts and tubes and apparatus and so on, in which they pumped in the gases that they knew would have been here in the early atmosphere, the same gases that come out of volcanoes today. An atmosphere that did not include oxygen, by the way. They energized it with heat, with some liquid. They shot electric sparks in and so on. They let it cook for 7 days, essentially. This dark red sludge, it's a famous experiment. Look at this online. Appears when they analyze it, they find many of the basic elements from which living organisms are made, including amino acids and nucleotides and so on. You can see their role in these more complex organisms, phospholipids and so on. So, in other words, these guys were able to prove that making these basic building blocks of life was actually pretty easy. Okay, but that's not enough. That's not life, clearly, right? How do these things get more complex? The argument is, under the right conditions, these organic chemicals, amino acid, look, just a handful of atoms long, tiny little entity, begins to join together, right? Begins to join up into long chains. You can see these chains begin to wrap up into these more complicated balls of matter. Eventually, in the quaternary stage, you'll get at least 4 of these sort of chains coming together, and eventually they'll start to form some sort of membrane or skin. And what you're seeing here, evolutionary biologists would argue, is the beginning of a cell, right? A cell, a human cell. Where were conditions right for this to have taken place? Those same volcanoes that are driving plate tectonics may have been the ideal environment, right? There's no ultraviolet rays down there deep under the ocean. No meteorite collisions are really affecting that far down. They've got heat and other chemical elements coming out of the earth, right, to feed on, if you like. Plenty of water, plenty of chemicals. This is where most biologists that I'm aware of believe the first life forms may well have formed. May well have formed. Still not life as we'd understand it, right? Complex organic chemicals made from this organic material. They're taking in energy, they're adapting, right, and they're even reproducing in a fashion. But inaccurate reproduction. So they can't preserve complexity, they can't preserve or pass on advantageous adaptations. So the key to accurate reproduction has to be, right, how do you precisely reproduce something like us with billions and billions of carefully arranged molecules? It's the genetic code, DNA, the molecule of life. Again, most biologists I read are not really absolutely certain yet how DNA evolved. We know how it works, right? And I'm not going to give you a scientific account here, but if reproduction is too perfect, adaptation and change is impossible. If it's too imperfect, then you can't retain this information you need, right? DNA achieves this almost miraculous balance. Accurate copying, a dash of variation, the key to biodiversity. Now, a 2-minute history of life on Earth and then we're done. Here it is, 8 stages, right? You can see first organisms, some of them learn to photosynthesize. This increases oxygen in the atmosphere. We see the prokaryotic cell evolve into the eukaryotic cell, of which we are made of. the eukaryotic cell. Sexual reproduction, my students always get very excited when they see that, but it's really not exciting at all, I'm afraid. The emergence of multicellular organisms very recently. Some of them get onto the land, vertebrates appear, mammals, and that's where we'll stop. The earliest living organisms, prokaryotes, tiny, no nucleus, the genes are floating freely inside. This is the first organism that we think, archaebacteria, sort of green algae sometimes that you'll still see on stagnant ponds, sort of a distant relative. Well, and it learns, learns to photosynthesize. Some of these organisms rise to the surface of the sea and they learn, I guess, again through adaptation, to extract the energy of sunlight. They evolve a chlorophyll molecule, a green molecule, which all plants have, and they begin this process of photosynthesis, which changes the atmosphere of the Earth and creates a lot of oxygen. Right? So the oxygen produced by photosynthesizers is poisonous for most species, but more and more of these early archaebacterial life forms learn to exploit this new energy source. Right? And those that can use it flourish, become more complex. The first eukaryotic cells emerge. They're using energy now from oxygen and sunlight. Almost unlimited energy is available now. Their genes are now protected inside the nucleus, much larger, much more complex. Sex, here it is, unfortunately, boring. Most of them just cloned, but then at some stage, some of these eukaryotic cells began to swap genes before reproducing. The result was more variation in their offspring, right? And this accelerates the pace of evolutionary change. It's a very slow winding up of the pace of change here, right? The first multicellular organisms appear. For the first 3 billion years, all life is just these single-cell organisms. In fact, until quite recently, most biologists believe that life began about 600 million years ago, because that's when we've got good evidence of multicellular organisms. We now know, because we're able to see much, much smaller fossils and so on, we now know that life began maybe 3.8, if not earlier, billion years ago. Some cells gather together in societies like these tube sponges, for example. Some of the cells become specialized, become more dependent. Right? So all these various cells begin to play different roles in what becomes a larger single organism of many cells. The first vertebrates, animals with internal skeletons, appear about 500 million years ago. They may have looked like this little fish, no heart, no brain. Didn't need it. Some get onto the land. I mean, how tough is this? Supplies of water have to be found. You've got to evolve, think of a crocodile skin. You've got to evolve a really tough skin to prevent excessive drying. How do you protect your eggs and offspring now, and so on? Plants probably got there first, more than 400 million years ago. Giant tree ferns, for example. Then huge insects, dragonflies that may have been 6 feet long. Then some land animals like Ichthyostega here that get up on the land, early forms of amphibians, about 370 million years ago. In the final stage, mammals appear. Warm-blooded, they feed their young with milk. Sounds familiar. They had fur. First mammals are very small, the size of a shrew, a little mouse, right? They're living in this world dominated utterly by dinosaurs. These things are scurrying around in the undergrowth. Morganusodon may have been an example. There's a wonderful David Attenborough Life on Earth program that begins with him holding this little Morganusodon fossil and a modern-day shrew and mouse and say, really, this is where we come from. And then the massive collision, as you know, and the dinosaurs are no more, literally. Not wiped out overnight, but wiped out quite quickly. This allows these other smaller animals that are not as damaged by the change in climate, right, as the dinosaurs were, to survive. And one group of mammals evolves into a tree-dwelling animal, a primate. They need 3D vision. Again, think about your own eyes here. They need large brains to process visual information. They need hands that can grip, Without any of these abilities, which have evolved because of the environment they're in, they would fall out of trees. And all the scientific evidence we have now today suggests that we are descended from these primates. Bonobo chimps, very close relatives of ours, also descended from this ancestor. We share, I'm sure you know this statistic, 98.4% of our DNA is identical with that of these little guys, right? So this is the argument. 7.5, maybe 8 million years ago, as I'll pick up with you next week, we all shared a common ancestor. And then evolutionary radiation occurred along slightly different paths thereafter. Wow. That's not bad. So 13.7 billion years, right? And humans, I promise, will join our story next week and be with us almost till the end. Now, you might think that a mere 200,000 years of human history is going to be a piece of cake. But in fact, that will not be the case. Because human societies are so complex, I think you could argue quite strongly that explaining the evolution of human societies is more difficult in a way than some of these. No, I don't want to downplay the work of scientists, but as difficult as what scientists have done in coming up with these extraordinary paradigms, which have a massive amount of evidence, right? Which fit so much data, and which biologists in China or Australia or India or the United States accept, for example, as the best possible model we have at the moment. So next time we'll bring the modern creation story up to date, and then we'll take it off into the distant future when we conclude in 2 weeks. Thank you, folks. Thank you. Happy to take some questions, so long as they have nothing to do with how many members of the House of Representatives they are. What else? Separation of powers, first 10 amendments, the Bill of Rights. I'm sorry, yeah.
Could you help me understand the difference between sun and stars? Are the stars just the same as the sun, but they're smaller, more distant? Help me understand.
The stars are, well, our sun is a star, a middle-sized star, and everything you can see out there is another star, right, of various sizes. Of course, because they're incredibly distant, they seem small, but every piece of light you see out there is essentially a star like our sun, very, very similar. Right? Some may still be first-generation stars made only of hydrogen and helium. Many others will now be second-generation stars like our sun. All those other complex elements were involved as well. But no, this is what staggered people even back in the, 12th, really, I think Giordano Bruno, this astronomer monk in about the 13th, 14th century, I think, first started to speculate, could everything we see out there be a star, just like our star? And it was just so mind-boggling that it took Copernicus and Galileo to really say, yes, in fact, that is the case. So yes, that's what everything you see is a star. Yes, ma'am?
If the age of mammals began 65 million years ago, and we know the instance of useful mutations in animals and mammals, has anybody ever done a calculation to determine whether 65 million years was enough time to go from the shrew-like creature to the vast diversity that we see today? Is there enough time? 65 million years enough?
Has that been long enough for the sort of diversity that may have come from the mammal population to have taken place? As far as I know, yes, that's been tested many times and calculated by geneticists. And I don't know, do you know the answer to that? I'm sorry, I didn't mean to put the ball. No, sorry, I won't put you on the spot. No, there's real scientists in the room, so I'm cautious in my responses. But as far as I know, very careful genetic mapping and dating these changes has taken place and been calculated.
What I'm saying is, we know the incidence of useful mutation is fairly small.
Mm-hmm.
Is there enough time to go from 65 million years? So I'd be curious if you could direct me to wherever those calculations are found.
Well, let me look into that for you and see where but that's the sort of the standard argument, the standard model in all the biology books that I read, that is enough time for these mutations to have taken place. I can certainly give you some sources that I use. Be glad to. In fact, this goes for everybody here. I've had some great email exchanges this week. You can easily find my email address through the Grand Valley website. If you want to engage in further discussion, delighted to do it. So,
two questions. One with the red spectrum. If all we're seeing is red, that tends me to believe we're at the center because everything is going out. Don't we have to be seeing incoming also? Not at the center?
The closest galaxies to us, we do see Andromeda, for example, is shifting towards the blue end, right? The closest one's in. But the way the astronomers I read explain it is that wherever you were in the galaxy, you'd see things flying away from everything else. So it's not that we're at the center, no. Although it almost sounds counterintuitive to say that, but wherever you were in the universe, you'd see the same phenomena, is the way I understand it.
Second question. I understand that the Earth is the only planet with plate tectonics. What would be the reason that we are the only ones?
Well, it's geologically alive. I mean, the only other planets we've really studied in any detail are those that are fairly close to us in our own solar system. And now some of the moons of Jupiter are active also, right? So, but most of the closer planets that we've been able to study in any detail seem to be geologically dead now. If they once had internal radioactivity, which they must have had, and volcanic activity, it seems to have long finished. So that process depends on these geological processes continuing within the planet, and ours is still alive. So I think that's the reason. I wouldn't say that there have not been, that there wasn't volcanic activity on some of these other terrestrial planets. I'm sure there was, but they seems to have stopped. It's dormant in some way. But have a look at some of the moons of Jupiter, Io particularly, where some incredible volcanic explosions have been recorded. So who knows what impact that might have on the surface of that moon. Yeah, good questions. Wow. Oh, I saw this man first. Then. Yeah.
I'm curious, where did the heat in the Earth come from? You were talking about these clouds of matter, and I think you mentioned ice, they coalesced into planets. Okay, so what caused the heat in the Earth?
Yeah. The standard argument there is that the terrestrial planets, that is the inner planets that are made essentially of rocks and heavy metals, the outer planets are made of frozen gases. They're too far away from the sun to have, so they froze essentially. But the terrestrial planets contain a great deal of radioactive material that was intensely hot anyway, material that was created out of the supernova, plus the intense pressure that's continued on the planet, plus heat coming from meteorite collisions as well, that these three causes were sufficient, right, for the Earth to reach the temperature required for differentiation to take place. So internal radioactivity, which is essentially a product of the supernova, the pressure created by the gravity that was crushing the planet particularly, and these continuous collisions. So that's, again, the standard model that you read in all the astronomy and textbooks. Man, yes?
You said that before 13.7 billion years, we know nothing. Are there scientists today who are attempting to move, to go beyond that 13.7 billion years, or are even speculating on processes or methods or technology to try to do that?
Yeah.
Or do you think that that's just a blank wall that we've hit for the foreseeable future?
No, the answer is both, because a lot of people seem to have, well, I wouldn't say stop speculating, but for a lot of people that seems to be an end point that, as you say, a blank point that we just can't get past. But of course, there's incredible speculation going on out there. The multiverse theory, I've got a couple of colleagues who are astronomers at University in California who articulate strongly the idea of a parent universe that's giving birth to other universes like ours, other parallel universes and so on. Multiverse theory has been quite well worked up in the last year or so. Last few years, I should say, last 3 or 4 years. Others as well, but I think it's safe to say there's a general acceptance that although we want to keep speculating, theorizing as much as possible, we have hit a wall there at the moment, right? And Stephen Hawking and others make the same argument that even with the most advanced mathematical calculations, and I can't explain this to you, but we do hit a point where the calculations stop working. It's almost like coming down to the sharp end of a pencil, and we can never get there, and somehow it wraps back around, and the math just doesn't work at that point. So I think we have to accept that's the current limit. Although, of course, brilliant minds are out there speculating all the time. As for the technology, I can't imagine what technology would allow us to look beyond the beginning of the universe. I can't imagine. But I bet Microsoft's working on it right now. Yep. Yes, ma'am.
One more.
See you, John. See you, Bob. Good to see you.
One more question. I read somewhere that, say 20 billion years from now, the Earth still exists, that the stars at night will be so bright it will be almost like daylight because the stars haven't had enough time, the light hasn't had enough time to reach the Earth. Is that
I haven't read that. That's really interesting. What, the light from more distant stars, I guess, because the light from closer stars is...
It hasn't reached us yet, so that the night sky far into the future will be almost like daylight because of the stars.
I'd be very interested where you read that. That's very interesting. No, I haven't. I personally have not read that. It makes some sense. I think early speculation said if the universe was infinite, there should be an infinite amount of light up there. I mean, because all these stars would be so bright. What impact the fact that the galaxies are flying away from us might have on that, I don't know. Whether the light will catch up with the expansion in the other direction. Certainly, as I mentioned, closer galaxies like Andromeda is going to move towards us, so that might feed into that idea. Yes, sir.
If 13 plus billion years ago there was this one particle that caused the Big Bang, is there any discussion on a second Big Bang? If there was a particle back then, could there be another one somewhere in the future?
Sure.
Happen all again.
Lots of speculation on that. Lots of speculation that gravity will win out over inflation, our universe will stop expanding and go backwards, at which point, get your mind around this, time will run backwards, so just conceive of that somehow, and eventually everything will come back again to a tiny subatomic particle, and there'll be a big crunch, and then a big bounce, and it'll go off all over again. And this might be the 243rd universe that we've lived in. But I will tell you that the most recent evidence from Hubble suggests that's not likely to happen. That expansion, though slowing, will probably continue. But whether there are, I mean, I've got wonderful books suggesting in every black hole out there, there's another universe that all began as a tiny particle. So, again, you reach a point in the end where your mind just says, what? You know, huh? But these are great questions. You also get a sense, I think, almost of how, we were talking about this before, Craig, how science and almost a theological perspective start to wrap together, not related to any specific religion or faith or anything, but so many quantum physicists seem to speculate on the mind of God, even however they sort of start to understand that. But no, on those sort of scales, I'm afraid my mind begins to warp out. Yes, sir.
Have you seen any studies, we hear about everybody's going back to the beginning. Have you seen any studies about the end?
Yes.
It took 13.7 billion years to get to where we are. And if, the lunar forces and the tilt of the Earth that were off less than 1%, it had to get to the point for perfection for us here. Is it still going the other way now? Is there a demise? And I haven't seen too many studies on that. I wonder if you had any information on that.
Yes. Look, if you're able to come to the last presentation in a couple of weeks, we'll deal with that in some detail. We know, we're pretty confident now we know what the ultimate fate of the Earth will be. It's very much tied up with our own sun, and when it would start to expand dramatically in the sort of death throes, and all life on Earth will be zapped off, and all the seas will disappear, and our planet will be absorbed into the sun. And it's not a very pretty picture, but you've raised the question. We know what will happen to our entire galaxy, and I'll offer you, I'll give you the latest thinking about the ultimate fate of the universe as well, a couple of 100 billion years from now. And it's, again, a pretty sad story, the heat death of the universe. It's if you can stick around for 2 weeks, I'll give you what I know of those details. Sir?
When you talked about the origins of life kind of happening near the volcanoes, there's some strange life forms that live in these very hot temperatures and these very, what we normally consider to be toxic
Definitely.
substances. Is that the kind of environment that would be the best example today of what?
That's a really good example of all these bizarre creatures adapted to this extraordinary environment so deep down that, you see in Jacques Cousteau movies or whatever. I think that's a nice example of just the extraordinary diversity that's involved in that particular environment. But of course, you're talking there about much later multicellular organisms that, but it's that environment, the very deepest parts of the Earth, with this sort of toxic chemical and heat mix, which most of those organisms, some of them certainly would still find useful today. Another way of thinking about it is some of the organisms you find in hot springs and Yellowstone and places like that as well. Some of the organisms that are adapted to that sort of quote-unquote poisonous environment as well may resemble some of these earliest organisms also. Yeah. Yes, sir. How are we going for time, Craig? Okay. Sir.
It's a compliment to us that we evolved away from those conditions to these conditions.
A compliment to us, you think?
Yeah.
Yeah. How do you mean?
Well, instead of saying that how could those creatures evolve to live down there, maybe we started there and we evolved to live up here.
Yeah, sure. Well, clearly from that account, we are descended from a long line of animals who were able to get out of the oceans onto the land and so on, and eventually one of those groups, we evolved out of one of those groups. Yeah, for sure. Yeah, it is a compliment to us, I guess. Yes, ma'am.
It seems to me that, if I heard you correctly, that evolution and adaptation has taken a lot of time.
Mm-hmm.
So in our current culture and our current global situation where there's a lot of interconnectivity between cultures, do we have enough time now to continue to evolve as a species?
Good question.
Kind of address that issue of fitness.
That's a really good question. We know that the environment is continuing to change. We're facing potential global warming, all sorts of issues. That will clearly affect most animals on the planet and most organisms who will have to adapt in some way to the changing environment. Whether we need to keep adapting is, again, a question that all the biologists I read are somewhat divided on, that we will see micro-adaptations, but because of our unique ability to almost create artificial environments or create an environment that suits us, has that somehow interfered with natural evolution, right? Because we now use cultural in the very broad sense, which includes technology and so on. We adapt culturally now through technology to the environment and even force the environment to suit us to a certain extent. Whether that will hold up if we see massive global warming and I'm sure our technology will keep evolving to allow us to survive in those new environments without having to go through too much physical change. There won't be enough time to go through enough physical change to cope with that. But have we somehow circumvented our own susceptibility to natural selection to a certain extent through our ability to create technology now, right, to make the environment suit us? For all the other animals, the global warming that we've probably created, they're going to have to deal with that through Darwinian mechanisms, if that helps answer your questions. Very good question. All very good questions. Wow. Good thing I'm wide awake and I haven't been in Detroit since 4 o'clock in the morning. These are great questions. I'm so delighted to talk to you about them all.
Well, Dr. Benjamin, I'm sure we'll stay for a few more minutes if people want to talk separately with him. I did want to, before concluding tonight, call your attention to 2 programs that will be occurring in November beyond the continuing lectures here. One is a luncheon meeting on November 10th at the Amway Ground Plaza, where Eva Cheng, who leads Amway's operations in Greater China and Southeast Asia, will be presenting. This is a jointly sponsored between the World Affairs Council and Inforum. She will be particularly talking in this session on managing in Asia, and particularly as a woman managing in Asia. And she was a captivating speaker when she appeared here last spring. I've known her for 20 years, and she is just a spectacular manager and leader in their operations throughout Asia. That's on November 10, and also on Tuesday, November 30th at the University Club for a program at 6:15, and there's a reception preceding it. There'll be a debriefing on North Korea. I think Dick Gauthier is here this evening, or at least right there.
He's hiding.
He's hiding. He didn't put the hand up. He didn't want to be naturally selected. But he took one of the World Affairs Council trips to North Korea, and he will be talking about that trip and about what he found in North Korea. So we're looking forward to that. Everyone is welcome to that as well. There are brochures like this out at the table as you leave. So I'd encourage you to go to both of those, and I would encourage you to come back next week for a mere 250,000 years. And then the whole future in week 4. So good night. Thank you for coming, and we look forward to seeing you next week.
Thank you, Carter. Thank you, folks.
Thank you,
very
sir.
much. That's great. Thank you so much. Thank you. Boy, you've just got to cover North